so this is the fun part of our series of videos on, explaining the mysteries of quantum physics and relativity. Now we're going to talk about the quantum mysteries, and actually why they are not mysteries at all. This is so exciting. Okay, you remember we defined states, the state of a particle or of an object. But I would like to differentiate between the classical states, states in classical physics, from the state in quantum physics. In classical physics, the state of an object is composed of all the parameters which can define and can be measured and which will characterize that object, at some point if it varies over time. And that means that to every state, there is a definite value for each parameter, each property of the object, and that can be measured at any time. Okay, so that's the usual classical way of talking about states. Now, in quantum physics, it's a little bit different, and here we're going to talk about states called pure states, which means basically that these are states where we know as much as we can, everything about the state of a particle. I won't go into the details, but, let's just call it a state. And the state of a quantum object is composed of all the information available for that state, pure state. And what that means is that for a given observable property, I call it omega here, some of the states can give the exact value of the observable. And we'll call those states an omega state, for that observable omega. Like, for instance, the observable could be the mass, or could be a position, could be a momentum, could be a spin, whatever that means, etc., etc. But there are also other states, states where you are not in an omega state. And that means that you cannot measure omega while you are in that state, for various reasons. But what you can do is you can calculate the probability to be in an omega state the next time you will measure that omega property. Okay? So two types of states as opposed to, the classical physics. Let's keep that in mind. So in order to be able to experimentally measure, that means in the physical world, the value of an observable property omega, the object must be in the omega state, okay? And finally, we can say that, for a given observable property omega, there are n omega states, one for each value, one for each possible value that you can measure for omega. All right? Okay. Now, how can we define the mathematical object that would be isomorphic to a physical quantum state? Well, the state in the physical world, has certain characteristics, as we've seen. That means, a bunch of elements that characterize the object. Okay, like space coordinates, momentum, mass, electric charge, spin. Again, whatever that means, etc., etc. But in the mathematical world, it implies additional characteristics. For instance, we want to measure elements of the states, in the mathematical world, the same way we can measure them in the physical world. We want to be able to tell the differences between states, to be able to compare them. And in a stable, not changing environment, we want this difference to stay the same, over time, or when we go from one state to another, if you don't like the word time here. I wouldn't blame you. Anyway, so we want the mathematical world quantum state to contain a bunch of characteristic elements, to be comparable to other states, which means we need to be able to express differences between states. We want it to be measurable, and we want it to stay the same relative to other states. So for the first characteristic here, in our mathematical world, we want an object that looks like that, where you have a bunch of characteristic elements here called x1, x2, x3, like, the mass. Well, they will correspond to the mass, a position, a momentum, whatever. And you can write it this way, or you can write it this way. Okay, so pretty flexible. Next thing is we want to compare states. That means we need to be able to make a difference, So we have to define the difference between state A and state B in the mathematical world. And that means we need an operation to add states, but also an operation to multiply states by a number or a scalar. And so that's what we need to do. And it happens that the mathematical objects that can be added together and multiplied by numbers like this are called vectors. And vectors also happen to have, to contain a lot of elements just like that. So it's a perfect fit, okay? Now, we also want the vector to be measurable, okay, to determine how different two states are, And for that, we need a three-step process. First process is to use the so-called inner product, which is a very key function, very underrated, in the mathematical world. It's very powerful, though. And with that, we'll be able to define, how to measure the amplitude of a vector, or the length of a vector, if you wish. And then we'll be able to differentiate between two vectors, and that will be very key to understand what's going on. So let's take an example of inner product. The simplest one is the Euclidean inner product, also called a dot product. So in that case, you have two vectors like this, and the closer they are, and the bigger the inner product will be. Okay, so the inner product will tell you how alike the vectors are. So we'll see that's very powerful. So for instance, here the inner product will be very big, because they're pretty close to each other. On the other hand, here, it won't be very big. Actually, it will be negative, in that case. Now, what happens when you do the dot product or the inner product of one vector with itself? Well, in that case, it will tell you, what the amplitude of the vector is, what's, in that case, what its length is, how much, quantity of vector you have. That will be just basically the length of the vector. And that's something very useful as well. Now, let's see how we can use that to define the distance, which will tell us how to measure things. What we've just done before gave us the norm of the vector. But now, if we look at the difference between vector A and B, which will be this red vector here, and we use its norm that we just defined before, then it will give us, the amount of difference between two vectors. And if these vectors represent states, that will tell us the difference between states. Okay, so let's keep that in mind, because we'll use that fact in a few minutes. Okay. So the last characteristic here is that we want the state to stay the same relative to other states. In other words, the differences between states should stay the same all the time. And in mathematical world, this is called unitarity. Sorry, and it implies that any state can be expressed from the initial state in a linear way like this. Any state here is equal to something that may vary with time, but it's basically a number times the initial state. But that also implies, and we'll show that in the math videos, that the inner products are preserved. So the distance between different states, stays the same over time, and that's very key also. Now, to summarize, the states in the mathematical world, in order to be isomorphic to the states in the physical world, they must be vectors. And their set, the set of all the states, which is called a vector space, will have to have an inner product. And the combination of a vector space with an inner product is called a Hilbert space. And thus, a norm and a distance to evaluate states difference, because thanks to the inner product, as we've just seen, we can define the norm, and therefore we can define the distance between states. And so they also have to follow a unitarity law, as we just saw. Now, this is great, this is math, who cares? And especially you don't, because I know you watch these videos because it says no math in it, well, it's almost no math. But how does that explain, the superposition of states, mystery in quantum physics, or the wave-particle duality of light, what does it have to do with this? What has it got to do with it? Well, let's have a look. First, superposition of states. At the beginning, when quantum physics was introduced by Einstein, Heisenberg, and others, there was a lot of controversy, and actually people like Schrödinger and even Einstein, disagree with Heisenberg conclusions, which unfortunately were correct. And Schrödinger's, used a thought experiment where he showed that with those conclusions, you could say that, a cat would be at the same time alive and dead. At the same time, yeah. And there was another experiment which was over 100 years ago, old, by Young, that showed that the photon could go through two slits at the same time. This is crazy. So it could be at two places at the same time. And that didn't make sense, okay? And so we'll look into the Young experiment in more details in a few minutes, but that was crazy. So this was this superposition of state syndrome, Now, in order to resolve that and to answer and show that this is not a mystery, we have to remember the peculiarity of the physical world quantum states, that there are some states which are omega states where you can measure the observable property called omega here. But there are some others where you can't measure it, okay? And you will be only able, as we'll see, to determine probabilities of what you will measure next time. And that's, something very important to differentiate from classical physics. Now, of course, because we want our mathematical world to be isomorphic to our physical world, well, we must see the same behavior in mathematical world states, and actually we do. Let's look at it. The states are vectors, okay, but the vectors can be expressed in a basis, in the mathematical world. What that means is that any state can be expressed as the sum of various states called the basis vectors here, with some coefficients here. Okay, that's almost the definition of a vector space. Any vector can be expressed like this. Now, in the math video, what we'll show is that this Sk here, S1, S2, Sn, they actually correspond to the omega states we talked about before, where we can actually measure something. And so that means, for instance, if you are in state S2, you will be able to measure a value V2. Okay, and same for S1, Sn, etc. All the possible values that you could measure. Now, the other thing it will show in the math videos is that these coefficients here are actually the inner products of this state with each of these states here. In other words, for instance, P2 will be the inner product of this state here, the current state, and the state S2, where you will measure the value V2. Quite interesting. Now, remember what the inner product means. If it's very big, it means that the S2 and S states, for instance, are very close to each other. That's interesting. So let's remember that. So let's remember the two important points here. First, a state can be decomposed as a sum of omega states, states where you can actually measure things with some coefficients here. And two, those coefficients are in fact here inner product. For instance, this coefficient here, P2, would be the inner product between S and S2, actually S2 and S. Okay? And we'll see where it leads. Very interesting, because there's this guy, named Born, a physicist, it's about the same time, Einstein, etc. and he had an intuition, thinking, let's see, those coefficients here, okay, they're inner product, but inner product can be complex numbers. So, I had this intuition that could be, they could be probabilities, but they can't, because probability is just a number between 0 and 1, and it's a real number. It's not a complex number. So, but if I take the module of those coefficients and square them, then all of a sudden it becomes, a real number that I can use as a probability, and it actually works. And that was his intuition, and he did actually work, In other words, when you say P2, S2 here, that means that if you're in state S, the next time you're going to actually measure the observable corresponding to that state, you will have a probability which will be P2 square here to be in state S2, which means you will find value V2 corresponding to that state. And that's very interesting. But why is that intuition true? Well, I won't give you a proof, but what I can do is give you a good intuition of what's actually going on. So let's look at it. First, the bigger the pK, the more S is like SK. You remember that I call it the inner product syndrome. When the bigger the inner product, and the closer the two states are. Okay. Now, as we saw, pK cannot be a probability because pK are complex numbers. However, Born said, well, if I pick this number, then it actually works. But let's see what it means. This means, the square product of the inner product here. But this, for a complex number, would be equal to this. And what that means is that SK is very similar to S, and that S is very similar to SK. That sounds a bit bizarre, but it's actually not always the case, of being SK S equal to SK when it comes to complex numbers. This is actually the complex conjugate. If you want more details on this, go watch my videos with the math-oriented explanations. But anyway, that's how you would describe or actually define the module of pK to square. That would be this. And so again, that means SK is close to S and S is close to SK. So the more S is like SK, the bigger the chance to measure omega is equal to VK after being in state S. Why? Well, my guess is because of the TUP. Because the least different the two states are, the more likely it is that you will go from one state to the other. Because you want a very smooth, small change, because of the TUP principle. Yes. And so that's a way to explain this. This, however, does not mean that S is equal to S1 and that S is equal to S2 and that S is equal to Sn. No. It means that S is equal to that. And that's it, okay? So actually, the Schrodinger's cat is not both dead and alive. It has some probability to be dead and some probability to be alive. And only when you look at it and you look at the result of the experiment, then you will see that it's dead or alive. Now, there's something I want to talk about, which is another mystery in physics called the wave function collapse. And for that, I will use an example, which is not really a quantum example, but it will give you a pretty good idea of what's going on. So the example will be the coin toss example. You throw a coin in the air, it's spinning like this, and then falls down to the floor, and you look at it, it's either head or tails. So what you can say, is while it's flying like this, it's in state S, and there's a certain probability that it will end up, when you measure it, in other words, when it falls down to the floor as being in S tails, well, for that there will be a 50% chance, and there will be another 50% chance of it being on head side. Okay? So that's when the coin is in the air. But what happens when you actually see it fall down and you actually measure it? In other words, you look at it. For instance, let's assume that it falls down on the tail side. Then the new state will be equal to 1 times S tails plus 0 times S heads. It's still the same equation, but of course the coefficient here have changed because you are not in the same state. You were in the state in the air, and now you're in the state on the floor, on the ground. So, of course, there is a change here. And that's what the physicists call the, wave function collapse. Well, when I measure, all of a sudden this function changes. No, it doesn't. It's a different state. Okay? And so in that case, you are in an omega state because you're able to actually measure the value of the coin side, While where you were here, it was still some uncertainty, but you could determine that there was a 50% chance that it would go on either side. So, there's no mystery, about superposition of states, It's not superposition, it's just the probabilities, And there's no wave function collapse either. Okay? So that's fairly, to me, easy to explain. Now, there's something we have not explained yet, and that's the wave-particle duality. Well, let's have a look at it. Okay, for that we have to have a look at the Thomas Young experiment, early 19th century. You can have a look at this website, which is well done to simulate different things, different experiments like this. Now, let's look at it. What Young did was that he was sending a light ray here, and here there is a slit here, okay? So the light ray would go through the slit here, and then here there is a wall, so it cannot go through this, So it will have to go through the slit here, and then there will be a screen here to see what happens. And obviously, if there is only one slit like this, and you send the light ray here, there will be some diffraction, but basically you will see a lot of light here, and then it will be much darker as you go away from the center of the screen here. Okay? No big deal. But then when you put two slits at the right distances, then what happens is that you see interferences like this. In other words, there will be a series of, a bright zone, then a dark zone, then another bright zone, and another dark zone, which is typical of periodic functions, wave functions, like if it was water here, or it was sound waves, which vibrates. And therefore, that's why Thomas Young said, okay, I've proven that light is made out of waves. But 100 years later, here comes Einstein who says, no. These are photons, not waves. But we see that. So, the physicists say, okay, well, it's both photons and waves. It's crazy. So what does happen? Okay, let's have a look again at our equations here. Let's suppose we're looking at the position observable. So in other words, we can say that a photon is at a given position. We mean it will be in a given state of position, and it will, as always, be a sum of all the potential position where it could be. Okay. Now the probability that it will be at some given position in the screen will be equal to this, as we just saw. Now, in the case of two slits, it will be the probability that it goes through the left slit and then arrive at that point, plus, which means or, the probability that will be going through the right slit and arrive to the same point. Okay? Okay. Now, in the math video that we'll see, we'll calculate those pK and we'll show, thanks to unitarity that we talked about before, that there are periodic functions. Yes. There are periodic functions, there are waves, but not the photons. The photons are not waves. The functions here, the probability of presence, in given positions will be waves. What does that mean? Well, that means that these coefficients pk are waves, and therefore, here, this is, by the way, a simulation, and the simulation says that when it's brighter, the pk is bigger, okay? And here you can see that the presence of a photon is very high here, and it's very low there, and it's very high again, and low, and high, and low, because of the interference between those two probabilities here, which both are wave functions, periodic functions, which explain why there is interference here. Okay? So what does that mean? Well, that means that the so-called electromagnetic wave, there are in fact flows of particles. They are particles, not waves, okay? But their probability of presence to some space, some position on the screen, are periodic functions, are waves themselves. And, when you throw a large number of photons, well, what does the probability mean? Well, it means the higher the probability, the more photons you have, and therefore the brighter the light will be at that place. And if the probability is smaller, then you will have less photon, and therefore it will be darker. And so what you see on the screen is just the position which is due to the probability of presence. Okay? So it's not that the photons or that light is a wave. It's just that the probability of presence at some positions are waves. Okay? So that's not the same thing. Okay? So light is not a wave. And what we call electromagnetic waves are not waves. They are particles, flows of particles. I'm not talking about field, which is yet another story. But, if we stay at particle level, there are particles, not waves. Okay, so there's no particle wave duality, mystery. Now, by showing why, not just how, we could show that, well, actually light is made of particles, not of waves. So we've answered that mystery, and Schrodinger's cat is not both dead and alive at the same time. There's no superposition of states. There is a probability it can be dead, and probability it can be alive. But when you measure it, then, it's either dead or alive, That's it. So there's no wave function collapse, as we saw. There's no mystery about that. It's just a change of state, And then we also saw why we can determine probabilities, of what is going to happen. And then the last thing is, this one is more tricky, actually. It says, it's called non-local causality. It says information cannot go faster than the speed of light. That's what Einstein told us, and he's probably right. But sometimes it looks like it does. It doesn't, but it really looks like it does. And it's kind of a mystery. And we'll try to give some explanation about that in the next video. Oh, this is so exciting. Okay, see you in the next video, hopefully.